In question 4, the first thing you're told to do is to solve these three simultaneous equations. Now, first of all, these equations are equations of the plane, so to speak. A plane just being a big flat sheet that goes on forever in all directions. So, for example, here's one plane, and the borders of this plane aren't really borders. I'm just looking at a particular slice of this plane. Now, if we have a second plane that isn't exactly parallel to that one, like this here, then what happens is these two planes are going to intersect, but not just at a particular point. They're going to intersect at this line here that's sort of highlighted in white there. We have three planes, so we're going to have another one here, the green one. And now you can see each plane has a line of intersection with another plane. So we have the one we had before, but with the yellow and the red. We have another intersection line between the green and the red, like that. And another one between the green and the yellow, which you can't really see beneath the red, but it continues this straight line between the green and the yellow here. Now these three planes intersect at a particular point that's highlighted in white there. But it's very difficult to work out exactly where that point is with the planes. It's much easier to work out a couple of lines of intersection first and use those lines of intersection to figure out the point of intersection. So that's the way you normally do these simultaneous equations when you've got the equations of the plane. So let me call these equations 1, 2, and 3. So first of all, I'm going to figure out the line of intersection between planes 2 and 3. And it doesn't really matter what order you do them in, or which two planes you work with. But I'm going to figure out the line of intersection between 2 and 3. And this is a lot like finding the intersection of two lines, in that you're trying to eliminate a variable. So I'm going to try and eliminate the x's from these two, because the 2x is the same in both cases. So I'm going to take 3 and then take away 2 from that. So it's going to be 2x plus y plus z. And then I'm going to take away 2, so it's minus 2x. The minus 3y is going to be plus 3y. And a minus 2z. And that's equal to 5 minus 2. That's the right hand sides of these equations. So those two x's are going to cancel, and I'm left with 4y minus z is equal to 3. And I'm going to call this equation A. I could call it equation 4, but I find this kind of distinguishes it a little bit better. So I can't do anything more with this. I have a y and a z in there, and I just have to leave it like that. So now I'm going to find the intersection of two other planes. This time I'm going to work with 2 and 1, so 2 minus 1. Again, I'm going to try and get rid of the x's, because I got rid of x's before, and also it just so happens in this case that getting rid of the x's is going to be probably the easiest, because it's 2x in both cases. So starting with 2, so I have the 2x minus 3y plus 2z, and I'm taking away equation 1, so that's minus 2x minus 8y and plus 3z, because I've got a minus minus, and that's equal to 2 plus 1. Again, minus minus, and these are just the right hand sides of equations 2 and 1. So again, my x's are going to cancel with each other. So I'm left with minus 11y plus 5z, and that's equal to 3. So I'm going to call that one equation B. So now I've got two equations in y and z, and this is a lot simpler. I can actually get this down to one variable and solve for that. So to do that, I'm going to take equation B, and I'm going to add on 5 of equation A. And I'm working with z's specifically because there's one z in equation A where there's 4 y's, and in equation B I have 11 y's and 5 z's. So the z's are the easiest ones to work with just because I only have to multiply one of my equations rather than two. So this gets me minus 11y plus 5z, that's equation B. And I'm adding on 5 of equation A, so 5 times 4y gets me 20y. And 5 times minus z is minus 5z. And that's equal to 3 plus 15. Again, that's 5 times 3 from equation A. So I can follow that through. And I get, let's see, 9y is equal to 18. So y is equal to 2. Now, using this knowledge that y is equal to 2, I can figure out what z is. So, going back to equation A, I now know what y is, so I can substitute that in. So I get 4 times 2 minus z is equal to 3. So that tells me that z is equal to 5. So now I know what y and z are, so I can figure out what x is. So if I look at equation 3, again, it's just going to be the easiest one because I only have one y and I only have one z, so there's a bit less multiplication to be done. So I've got 2x plus 2, that's the y, and I'm adding on 5 from the z, and that's equal to 5. So I get 2x is equal to minus 2, and x is equal to minus 1. So that's the solution. That tells you that the coordinates of the point of intersection of these three planes are x is equal to minus 1, y is equal to 2, and z is equal to 5. Part B gives you the graphs of two functions. F is this function here, and g is another function which is just a straight line. And you have to find the coordinates of the points A, B, C, and D. So you'll notice that A, B, C, and D are all intersection points. A and B are where these two functions f and g intersect. C is where the function f intersects with the x-axis, and point D is where the function f intersects the y-axis. So I suppose the easiest ones to find out, first of all, are C and D. So at point C, it's the x-axis, so y is 0. I know that x minus 3, well, the modulus of x minus 3 is equal to 0. So I get x minus 3 is equal to plus or minus 0. Now, of course, plus or minus 0 are the same thing, so we don't actually need that at all. So we get that x is equal to 3. So the coordinates of C are 3, 0. Now, let's look at point D. Now, this is the y-axis, so I know that x is 0. So I take a look at 0 minus 3, and the modulus of 0 minus 3 rather. So that is the modulus of minus 3, which is 3. So that means D is at 0, 3. And that looks about right, because we know that C is 3 away on the x-axis from the origin, and it looks like D is about the same distance away from the origin in the y direction. So it should be in around 3. Now, figuring out A and B are a little bit more difficult, but again, it's just an intersection. So I know that x minus 3, well, the modulus of x minus 3, is equal to 2. So we have one scenario where x minus 3 is equal to 2, and another scenario where x minus 3 is equal to minus 2. Well, in this first scenario, where x minus 3 is equal to 2, x is equal to 5. And in this other scenario, where x minus 3 is equal to minus 2, x is equal to 1. So it's easy enough to tell which one is which, because B is further in the x direction than A. So that means that this is point B here, 5, 2, and this is point A, which is 1, 2. Now we're told hence or otherwise solve this inequality, and usually hence is quite a bit easier if you can figure out what the hence is. And in this case, we already figured out where the modulus of x minus 3 is equal to 2, and now we have to figure out where the modulus of x minus 3 is less than 2. If we take a look at our graph, that's all of this here. We know that everywhere to the left of A, the function f is going to be greater than 2, because you can see it's increasing. And everywhere to the right of B, f is going to be greater than 2, because again you can see it's increasing. And we know that at A and B, f is exactly equal to 2. So the only other place that we have to look at is in between A and B, which is where the modulus of x minus 3 is equal to 2. So using the hence, we can just go right to the end and say that 1 is less than x, which is less than 5. Because we already know that these points A and B are at x equal 1 and x equals 5. So this is a really easy couple of marks you can get here.